So today we are going to talk about graphs. So we have already seen trees in the course, and today we are going to talk about graphs and how they are useful. First, let me try to motivate them. So consider the following simple problem of lecture halls scheduling. So what is the problem? The problem is you are given a number of lectures that are going to occur and with their timings. So suppose you have lecture 1 that occurs from 5:30 to 6:30 p.m. There is lecture 2, which is a really long lecture which takes place from 2 to 6 o'clock. And there is lecture 3 that takes place. So, so basically it's like 5 o'clock to 7 o'clock, and lecture 4, which takes place from let's say 1 o'clock to 3 p.m. Correct? Now you want to know what is the minimum number of lecture halls you need to provision. What is the maximum number of lecture halls you need to provision in order to be able to schedule all these lectures? Correct? So, so how do we solve this problem? You would, given just this data, you could think of one way to think of the problem would be to try to sort the data somehow, let's say on the starting points, and then try to see greedily allocate lecture halls, correct? So meaning you would allocate, the first lecture starts here, this is the first lecture, you give it lecture hall 1, and then where it, then take the next one to start, give it 2, and so on, correct? So this is one way of doing it. And in this particular case, if you do it this way, how much time will it take? You have to scan the list every time to find the next thing that starts, and so on. So it takes order n squared time. Roughly speaking, there are 2 loops, one which finds the next lecture, the immediately next lecture after the currently scheduled lecture, and you give it the first free hall, that is first free lecture hall amongst, let's say, amongst all the lectures, correct? So some heuristic like this you can apply, and in this case it does work. But there is a nicer way to think about this problem, which is to model it as a graph. Okay, so what is lecture 1? Think of lecture 1 as a vertex. So this is the vertex 1, vertex 2, vertex 3, vertex 4, correct? Now, does lecture 1, if lecture 1 intersects lecture 2, then you draw an edge between them. Draw an edge between them. Does lecture 1 intersect lecture 3? Yes, it does. So draw an edge between them. Does lecture 1 intersect lecture 4? No, so leave that alone. Similarly, lecture 2 to lecture 3, is there an edge? Yes, there is an edge. Lecture 2 to lecture 4, is there an edge? Yes, there is an edge. Then lecture 3 to lecture 4, is there an edge? No, there is no edge, correct? So this is what we call a graphical representation of the above data. Correct? We have abstracted out the information that was there about the timings, because that's not so crucial. Correct? So this is one way of abstracting out this. Another way could be you represent these lectures by intervals. Correct? So you say that lecture 1 is an interval from, you mark the times from 0 to whatever, from the minimum time is 1 o'clock. So let's say from 1 p.m. to the maximum time is 7 o'clock. So you map them into these 2, 3, 4, 5, 6, 7. Correct? And now you draw lecture 1 goes from 5:30 to 6:30. So it goes 1, 2, 3, 4, 5, 6, 5:30 to 6:30. Lecture 2 goes from 2 to 6 p.m. It goes from 2 to 6. So I will mark, I will call this 1, call this 2. Lecture 3 goes from 5 to 7 p.m. From 5 to 7 p.m. And 4 goes from 1 to 3 p.m. So 1 to 3 p.m. Correct? So this is another way to represent the same data. You can now even forget about the line that we had drawn, the timeline, and just represent it by, so sorry, this was 3 and this was 4. Correct? This was 4, yeah. So you can also represent this by just this without, so the intersections are important. Okay. Now these are two different representations of the same data, these two, and they are progressively more abstract. So this one is the most abstract, this one is less so, and this is the complete data. Correct? And now the problem we have to solve is to allocate the what is the maximum number of, what is the minimum number of lecture halls do we need to be allocated, to be able to allocate all the lectures. Correct? Are you with me?
Yes, sir.
So now in this representation, this is easy to do. Why? Because you can sweep a line from left to right and see how many lectures are progressing at one time. That is the maximum number of things that you need, maximum number of halls you need. So beginning you need 1, then you 2, then you need 1 again. At this time you need 2. Here you need 3. So 1, 2, 1, 2, 3. Then again you need 2 at this time, and then you need 1. Correct? So the maximum you need is 3. Yeah, tell me.
Sir, this is just a suggestion. In the graph interpretation, we could just color the graph, right? We could try coloring the graph.
Of course. So we'll come to that. I'm coming to that. So this is one way to represent data, and this is one way to solve it. Correct? The other way is to do a valid coloring of the graph. What do I mean by valid coloring of the graph? A valid coloring of a graph is allocation of colors from a palette to the vertices, so that I get different colors. Okay. So for example, you can call this, I'm not going to use colors, red, call this green. They are linked by an edge, so I have to give them different colors. This is blue. It cannot be red and it cannot be green because it's connected to both red and green. And now I can color this either red or blue. Correct? So for example, I color red. So 3 colors suffice. Correct? So now you would think that so basically I'm saying this color problem is a more problem, but more general graphs is much harder to solve than finding the coloring through this method in interval graphs. Correct?
So this is just number of the graph will be the number of lecture halls.
Yes, the chromatic number of the graph will be precisely the number of lecture halls we need to allocate the lectures. Correct? Chromatic number is the minimum number of colors you need to color the graph. Correct? Correct? This works not just for graphs which are intersection graphs of intervals, but for arbitrary intersection graphs. And they could be a lot more complicated. So in general, we do not know of any polynomial time algorithm to solve such problems. But for interval graphs, for lecture hall scheduling, there is a polynomial time algorithm, which is essentially this. Correct? In other words, the clique problem, another problem that you can solve is the size of the largest clique in the graph. Correct? And that is a bound on the, so you need at least clique many colors to color a graph. You might need more. So what is a clique? A clique is a set of vertices in the graph such that all a clique. So firstly, let me write this. RGB is an example of coloring the graph. And the minimum number of colors required is equal to is defined as equal to the chromatic number. Correct? Of a graph. And chromatic number is what we are looking for. Clique number is a lower bound on the chromatic number. So what is clique number? The maximum number of vertices in the graph such that they are mutually adjacent. Correct? So usually chromatic number is represented by chi of G. The clique number is represented by omega of G. And now it's easy to see that omega of G is less than chi of G. Why is that?
Because all the vertices of a clique must be colored differently.
Must be colored differently. So this is a witness to the fact that a clique is a witness to the fact that the chromatic number is at least the size of the clique. Correct? Okay. Now, is this inequality tight? Can you say that is W omega G always equal to clique number? Not, then can you give me a counter example, a simple counter example?
Sir, could you explain the above inequality?
Explain the.
Yes, sir. The omega G.
The above inequality. This one.
Yes, sir.
So if you have a clique, what is a clique? A set of vertices so that all the edges, all the vertices in it are mutually adjacent. Correct? So this is the maximum number of vertices. So you number the vertices 1 through omega g. Now, how many colors do you need to color these? You will color, suppose you color this with color C1, this with C2, this with C omega g. You cannot
Okay.
use less than omega.
Yes, I understood, sir.
Correct? So you require at least omega g colors to color the graph, which means that chi g is at least omega g. Correct? Now,
Sir, a triangle with a center, like a dot in the center, the dot is connected to the three vertices. That is the counterexample.
That's a counterexample too. So here, what is omega g? Equal to 4, chi g is also equal to 4. So this is not a counterexample.
Okay.
Sir, without the dot, is the counterexample.
So think
A
about
pen-
it. Tell me.
A pentagon is a counterexample.
A pentagon is a counterexample. That's very good. So, so why is it a counterexample? Because what is the largest click here? Is of a click of size 2, while chi of g you can verify is 3. Why? Because you have 1, 2. Suppose I want to color with 2 colors, but then this is adjacent to both things colored 2, and therefore this must be colored 3. Correct? So any odd cycle is has click number 2, while the chromatic number is 3. Correct? It's not a bipartite graph. You cannot color it in 2 colors and so on. Correct? So this is just to induce, just to motivate these parameters. I don't expect you to know them inside out. Correct? So now. Now the point is this chi of g is also occurs in one of the most famous graph theoretic statements, which is that chi g is less than equal to 4 for all planar graphs. And it's classically stated in terms of maps. So this is in terms of maps, it is the 4-color theorem. Correct? Which was proved in the 70s. So what does it mean? So what is a planar map? A planar map is what you would expect. It is a graph in which there are regions, and the regions touch each other in boundaries. We don't count. So here, these 3 touch each other. On the other hand, we do not count this as, so if you have a graph like this, then we can color this one and this one with the same color. These, because they touch only the vertex, they don't. What is the minimum number of colors you need to color the graph? Correct? For example, in this one, you would color this with color C1. Let's color this with C2. It cannot be the same color. Here we would, this is a 3-click, so we would color it with C3. But now we can color it with C1, and we can color this with C2. So actually, you see that in this graph, only 3 colors suffice. C2. So if you remove this edge, or if you add this edge, then you can color it with C4. Then you need 4 colors. At least it seems so. Correct? So the 4-color theorem says that 4 colors suffice for all planar graphs, and it is a horrendously hard theorem to prove, No short proof is known for this problem. Yeah. So
Sir,
you can handle it.
is there an upper bound for chi of g minus omega of g?
There's an upper bound for chi of g
Minus omega of g. Is
Is
there an
there
upper
an
bound?
bound? So is chi g arbitrarily larger than omega g? Is it I'll have to think about it. I'll tell you. Correct?
Okay.
Okay. So so graphs are ubiquitous. They occur everywhere. Planar graphs are also very common. They occur as maps. Naturally, we live in on the surface of the earth, which is a sphere or almost a sphere, and things on the surface are naturally planar graphs. Graphs may be planar graphs do not have a unique embedding. So you have to distinguish between the graph, which consists of vertices and edges, and its embedding, which has faces on this in this embedding. For example, you can take this graph and you can embed it like this, correct? So it's the same graph 1, 2, 3, 4, 5, 6, 7, and you have 1, 2, 3, 4, 5, 6, 7. So you can verify that the adjacencies are the same sets of vertices and edges work, but the representation on the plane is different, correct? Okay, what are other examples of graphs? What are other examples of graphs? There are, for example, in routing problems, so routes like road networks are, or airline networks are all examples of graphs, correct? And you can also do things like so here we must distinguish between two kinds of graphs, which are directed graphs and undirected graphs, but we'll come to that later. So another example is this course dependencies. So you have courses C1, C2, CK, and there are some dependencies, there are some prerequisites, some course is a prerequisite for another course, and so on, correct? And so that can be represented as a graph, correct? So now how do you formally define a graph? It consists G is equal to V comma E, where V is the set of vertices and E is the set of edges, and E is a subset of V cross V. And now we make several stipulations. Firstly, if E is symmetric, meaning UV belongs to E, if and only if VU belongs to E for all. So for all UV, if this is the case, then the graph is said to be G is symmetric, is undirected. Correct. So this is the definition of an undirected graph, that E is symmetric. What so the maps that we so many of the graphs that we consider, like the planar graphs we considered, are undirected. You can also have G is directed when E is not necessarily symmetric. For example, in coarse dependencies, it must be the case that the graph is directed because C1 is a prerequisite for C2, means that C1 must, so there is a natural direction from C1 to C2. It doesn't make sense to say C1 and C2 are prerequisites of each other. In fact, what in the case of these coarse dependencies, coarse, what is it called? Yeah, coarse dependencies. The graph is acyclic. Coarse dependencies, example of directed acyclic graphs. What does an acyclic graph mean? That if you start from a vertex and start walking on the graph, taking an edge out of every vertex you reach, then you cannot come back to the original vertex. Correct? Are you with me?
Yes, sir.
This also brings me to the small thing that we are dealing when we said E is contained in V cross V. Theoretically, we are allowing edges like I, U, U, correct? So these are called self loops, and usually we forbid them. So in simple graphs, there are no self loops, correct? Usually not present in graphs. Correct? Because for most of the applications, they don't seem to serve a purpose because you are just looking at the same vertex, doesn't model anything new. But in when you do algorithmically, they might prove to be very useful as a matter of fact. So we'll come to that. So now, what is the simplest question that you can ask about graphs? So the simplest question that you can ask about graphs is, I give you a graph G and two vertices. So suppose for definiteness sake, it is an undirected graph. Undirected graph and two vertices U comma V belonging to V or V of G. To make the vertices explicit, you write V of G, dependent, indicating the dependence on G, correct? So, and you have two vertices UV belonging to V of G. You want to know if there is a path from U to V, correct? So, what does this mean? We want to know if there is a sequence of vertices, let's call it U1, U2, UK, where this is equal to U, this is equal to V, and for all I, for all I in I belonging to k minus 1 is equal to, I'll often abbreviate k minus 1 as 1 to k minus 1. We have that ui comma ui plus 1 belongs to E. Now, if you are careful, you might say that in this sequence, we have not prevented vertices from repeating, correct? When I wrote path here and I wrote a sequence of vertices which goes from U to V such that adjacent vertices are edges. This doesn't preclude the sequence of vertices from being the vertices in the sequence being distinct, which is what we often associate with the path, correct? So what I have said is there a walk from U to V, correct? So now if there is a walk from U to V, can you prove that there is a path and vice versa? Just as a simple exercise.
Yes, sir. If there is a walk, then that is a path, so we're done. If there is a path, and we assume that for contradiction it repeats somewhere and there's no walk, but it repeats somewhere, so we can just ignore everything in between and it will be a walk and keep doing so.
Correct. By the way, just to interrupt this thing, somebody asked me that is there an upper bound on okay, forget it. Maybe we'll talk later. Yeah, about that. So I don't want to. Yeah. So yeah, that is correct. So there exists a path if and only if there exists a walk. There exists a UV path if and only if there exists a UV walk in G. Correct? That's what you just told me. Correct? So but they are different objects nonetheless. And now, how do you find whether there exists so how do you find whether there exists a path or a walk? So in order to do that, we would have to set up some notation and before we come to the algorithm, correct? So firstly, we would have to agree on a representation of the graph, correct? So this graph is something with vertices and edges. How do we represent this graph? So one very simple representation of graphs. So one very simple way to represent a graph is via adjacency matrices. Okay. So what is an adjacency matrix? So you are given a graph G equal to V comma U or V comma E. And now the adjacency matrix A, or often written as A sub G, is a matrix which is, so AG is a matrix with 0, 1 entries, and they are V cross V. Correct? So it is an N cross N matrix. Often we write V is equal to N, that is an established convention. that you take an n cross n matrix in which you put a 1 at the uvth spot. If so, you say that AG of UV is equal to 1 if UV belongs to E and 0 otherwise. Okay, so here we have made an implicit assumption that we identify the n vertices with the numbers from 1 to n. Correct? That V is equal to n. If you want to be more formal, you can write V as V1, V1, V2, Vn. And now you write AG of I comma j is equal to 1 if Vi comma Vj belongs to E and 0 otherwise. Correct? Are you with me?
Yes, sir.
So usually we conflate the two things and say that the vertices themselves are numbers from 1 to n, and then this is a matrix. So what is an example of such a matrix? So if you have, for example, let's take a small matrix. 1, 2, 3, 4. And now we make a 4 cross 4 matrix. This is a 4 cross 4 matrix in which, so I'll write 1, 2, 3, 4, 1, 2, 3, 4. And now this yeah, so 1 to 2 is an edge, 1 to 3 is an edge, 1 to 4 is an edge, 1 to 4 is an edge, 2 to 1, so 1 to 1 is non-edge because we have no set loops. 2 to 1 is an edge, it's a symmetric graph, and 2 to 1 is of course an edge. And so firstly, let me put all the self loops as zeros. And now I need to fill in only the super diagonal, the below thing is follows from symmetry. So 2 to 3 is an edge, yes. 2 to 4 is an edge, no. 3 to 4 is an edge, no. Correct? So this is a matrix, and we can quickly fill it by symmetry. So 1, 0, 1, 0, and 0. Correct? So now this is an adjacency matrix. Adjacency matrix. And yeah, so adjacency matrix A of G of this G, correct? Now you can have, here it's clear that the graph is connected. It's a small graph, you can do it by inspection. But in general, if you want to do reachability on such graphs, so I give you some graph which is a large graph, and now I want you to check whether it is connected or not. Of course, you can see here, these are not vertices. These are not vertices. You can see here that there is no path from 1 to 7, correct? But how would you do that if you are given the adjacency matrix? You are given the 7 cross 7 matrix. let's quickly draw it. 1, 2, 3. Let's just draw the super diagonal. 2, 3, 4, 4, 5, 6, 7. 6, 7. Correct. So this is a clique. 4, 5, 6, 7 is so 1, 2, 3, 4, 5, 6, 7. Yeah. So 4 to 5 is an edge. This is 4 to 4, and this is 4 to 5. 5 to 6 is an edge. 5 to 6 is an edge. And 6 to 7 is an edge. And the rest is all zeros. Correct? And you can fill in the transpose of it below. Correct? So given such a matrix, it is not immediate that
Sorry, your screen is not.
1 second. Now is it visible? No, not yet. Now is it visible?
Yes.
So while in a graphical small graph drawn on paper, it's easy to see whether two vertices are in the same component. When you go to matrices, it's not at all clear just by inspection whether the graph is connected or not. Correct? And here we have even separated out 1, 2, 3, so you can see that there is a 0 column between. There is some this thing. But suppose we relabeled this matrix so that this was 4, this was 3, and this was something. So 4, 5, and this was 2, but this was 3, and this was 2. Suppose the matrix given is like this, then from the graph given is like this, then from the adjacency matrix, it's not at all immediate that you will get you'll be able to find out easily what the connected components are. So now so I would like to collect suggestions for how to find whether U and V are connected in this graph. U and V are two vertices. How would you check that algorithmically? So suggestions.
So first we check the pointer at U, if that's 1, then done. If that's not, if that's 0, then we crawl up or crawl left. The sum of 1 or something.
So you are given this matrix, and now how would you do it? So you said something about crawling from 1, and suppose we want to know 1, 7. Now what do we do? Let me revert back to the original matrix, original this thing, because the matrix otherwise won't match. Now tell me. So what should we do?
No, sir, I don't.
Okay. Tell me.
Sir, I think we do have that. The graph is connected if and only if for some permutation of the numbers there is a 0 column. Is that correct, sir? Sorry, there should not be.
That there is no 0 column. No, that's not
sir.
true.
So there is some permutation of the columns. Oh, sorry, of the numbering. There is some numbering of the nodes such that there is a 0 column in the adjacency matrix. Is that correct?
I don't think so. For example, you can take just clique here and a clique here. So you have 1, 2, 3, suppose here, 3 clique. So in this case, what would you do? Which permutation would work?
Sir, does this work? I think this would work, sir.
Which one?
Because because the oh no, sorry, sir, sorry.
A naive
Yeah.
algorithm would be like to take the
That
go
means
down the column of
Huh.
7, find the first one, and then the first one occurs at 6. So we now go down the column of 6, and then the first one occurs at 5, and then we go down 5. Okay, so now 5 is
Okay.
connected with 4, but 4 is like all are 0, so it's not connected any further.
Good. But now suppose I connect 4 and 7 and 4 and 6. Now what do I do?
So 4 and 7 connect means like from 7, when we crawl down to 4, it will reach 4 directly. So we check then the 4th column. And since all 4 is not connected to 1, 2, 3, it will just stop.
But what is so special about 4?
No,
If
from
I-
7 we go down, like from 7 we
we
come down 1, 2, 3,
rename
4.
them,
The first one occurs at 4.
We call
Because
this
4
1,
and 7 are
we call
connected.
this 2, we call this 2, and we call this 4. Now what happens? What I'm trying to say is, like the other person was saying, permutations of these will not affect the graph. So anything which is based on going to the smallest vertex naively will not work, correct?
No, I mean, in the matrix, we have an adjacency matrix. It should have some labeling. After that, we can construct an adjacency matrix. So in the adjacency matrix, we get from the 7th, if we want to find the connectivity between 7 and 2. So we just
7 and
come
1.
down.
1 and 7 is what
Okay,
I want.
1 and 7. So just come down from 7 along the column, like 7, 1 is 0. No, 7 in the matrix I'm talking about, 7, 1 is 0. So it's not connected. 7, 2 is also 0. 7, I mean, 3, 7 is 0. 4, 7 is 0. So 6, 7, it occurs 1 at first at that point. So we come now to the 6th column. And
Okay.
then we check like 1, 6 is 0. So first one occurs at 5, 6. So 5 and 6 are connected. Then we come at the.
So how will you structure this into a algorithm? You have to
It
write.
will be an algorithm because we just take the, like, if 1, 7 is required. So okay, we can also start from 1. So, let's start from 7. So
7.
just we go down the columns of 7.
Huh.
Check all the 7, I, 7s, and when the first one occurs, break the loop, and then check keep this I and just start checking the column of I. But it will be very bad. Like it would be n squared by 2 complexity. In fact, yeah, n squared by 2.
Yeah. So so when you break the loop at which one? That is not clear. So you see 7 adjacent to 2 and 6.
Yes. Oh,
so which one?
I'm not talking about the graph. I can't think of the graph matrix right now. I'm talking about the matrix, from the matrix. When we will input the graph to the computer, it will be inputted as a adjacent matrix, right? Adjacency matrix.
Yes. So you can think. So you can think in terms of adjacency matrix, but
yes,
the adjacency matrix codes this graph with this labeling, suppose.
Yes. Okay.
So why I am saying this is often it makes sense to talk in terms of graphs rather than matrices. But we will talk in terms of both, and I will give you an indication of how to do it. This thing. So tell me, any more suggestions?
Sir, we could try to break the graph into components.
Okay, very good. How would you break the graph into components?
Like we start at vertex 1 and then see where I can go from 1. Like suppose I go to 2, then from 2 I see where I can go. And do this as long as I can so that I get a component of the graph.
So how would you structure this into an algorithm? You go from 1 to 2, And from 2, there is a way to come back to 1 or go to 3. And from 3, there's a way to go back to 1 or to 2. How do you organize this into a search?
Like a DFS.
Like a DFS. Okay, DFS could be one way. Are there, without using black boxes, can you tell me how to do it?
Without using DFS.
No, without using a black box. Can you explain the algorithm to me? The intuitive idea of the algorithm. Of course, DFS works, I know. Okay, so you are saying we could do DFS. Are there other suggestions? So one very simple idea that as mathematics students you would like is via matrix powering. Can you think of how to do that?
Sir, the graph will be connected if and only if all the entries of a to the power n are non-zero.
Yes, but I'm not asking for connectivity of the graph. I'm just asking whether u to v path is there or not. The graph might be disconnected, but these two might be connected still. Like in this 1,
Okay,
2, 3, 4, 5, 6, it might be that 1 and 3 are in the same component. So there's a path from 1 to 3, but there's no path from 1 to 4.
So I and j are connected if and only if the ijth entry of a to the power n is non-zero.
If the ijth entry of a to the power n is non-zero.
N is the number of vertices.
So do you have self loops? If not, then just take this graph, a path 1, 2, 3, 4, 5. What is the matrix? It will look like it will be a super diagonal matrix. These will be 0 and these will be 1. Correct? Am I correct? These are all 0. Correct? And I'm not drawn it's a symmetric graph, so there are these things below and so on. Correct? So so now if you compute, oh, 1 second, sorry. One second. So if you consider a to the power n, a to the power 5, and you are looking for connectivity between 1 and 4, you would find that a to the power 5 of 1 comma 4, in fact, a to the power 5 of any I comma 1 comma I is equal to 0. Do you see that? Hey, so in this graph, a to the 5 of 1 comma I is 0 for all I. Isn't that true? Hi, are you there? The person who suggested this.
Yes, yes.
So a to the n directly does not work.
So how about checking all the, I mean, so for some n, say, for some n it is non-zero.
Yes, that could be one way. The other simple way is just checking whether I plus a to the power n is non-zero, correct? Basically, I'm saying you add self loops. N minus 1, in fact, would work. So you add self loops here. And despite, so what is the advantage of adding self loops? That if you reach a vertex, you will stay also you will continue to stay on that vertex, correct?
Yes.
So this u comma v is not equal to 0. Correct? Now, what is the complexity of this algorithm? Can you tell me what is the complexity of this algorithm?
N log n.
N log n. Why is it n log n?
Because we can like binary exponentiate the matrix.
Correct. And how much does one exponentiation take? How much time? Going from I plus a to the 2 to the I to I plus a to the 2 to the I plus 1. We're saying these i's are log n in number. Yes. But what does 1, which is equal to I plus a 2 to the I whole squared, how much does this operation take? Does this take linear time?
We could have just diagonalize the matrix then.
You could diagonalize it if the matrix is not diagonalizable.
No, I plus a will be diagonalizable because
Okay,
also
but
diagonal
then,
elements are one.
okay, fine. But what is the complexity of diagonalizing a matrix? You tell me. So you would at least have to multiply together two matrices to diagonalize it, correct? The complexity would be at least that much as multiplying two matrices.
Yes.
So naively, if you multiply two matrices, it takes order n cube time. Correct? Naive algo to multiply two matrices takes order n cube time. Correct? But you can do it slightly better. You can do it in something like order n to the omega time, where omega is 2.38 something. Correct? Yeah, all that can be done, and then you can do this like this binary exponentiation in steps of 2, in powers of 2. That would take order n to the omega log n time. Correct? So can you do better through a simple algorithm? And moreover, here we have not taken into account the length of the input. So why are we powering? Because I missed that, because if you do I plus a to the n, then you compute the number of walks in this graph from of length at most n, correct? So I'm just trying to indicate that there are natural ways of doing things which are too expensive when it comes to actually implementing them. Other way to do it is to compute this I plus a squared plus a cube plus so on, plus a to the n minus 1, which as a geometric series you can see is I plus a, I minus a. So if you write it, because they commute, so you can write it as I minus a to the power n into I minus a inverse, correct? So you can even verify that I minus a inverse suffices, correct? If you compute I minus a inverse u comma v and that's non-zero, then you know that there is a path from so why do we have to go to a to the n minus 1? You can go to this thing after dividing by something like this. Correct? So this is a to the power n minus epsilon a and that is just epsilon A whole inverse, correct? So if you can compute the inverse, you can do this, correct? Notice
Sir,
this. Sorry, tell
I
me.
don't understand why this should work. Like,
Okay, so let me explain. So look at I plus epsilon A, correct? What does the UVth entry of this say? This says that for U not equal to V, is there, what is, so if there is a edge between them, you put epsilon, otherwise you put 0, correct?
sure, sir.
What does plus epsilon squared A squared term say? What does A squared tell you? A squared tells you that there is a path from U to V, from U to W, and W to V. Then AUV will be 1. If there exists W, or the number of W's such that AUV, WV belonging to E. Correct? That would be the coefficient of A squared UV. Is that true?
Sure, sir. Yeah, makes sense.
Yeah, so E union, where I have E plus, where E plus is E union U comma U, all the self groups, correct? And similarly, A cube, no, sorry, what am I, I'm mixing things, sorry. No, this is just E, this is just E. Correct? So, what does A cube UV give you? Is equal to number of U2 comma U3 such that A U comma U2, U2 comma U3 comma U3 comma V belong to E. Correct? And belong to E and belong to E and belong to E. Correct? Do you agree?
Yes, sir.
And so on. Correct? So these are basically the number of walks from U to V, which so of length 3. You go from U to U2, U2 to U3, and U3 to V. And this epsilon factor we have added just to make the series converge. Summation epsilon A whole to the power I converges for sufficiently small epsilon, like epsilon equal to 1 by n, because then the matrix is strongly dominant or something, correct? So this series sums to I minus epsilon A inverse. And so there is a path if you can invert the matrix. An inversion of the matrix is not much harder than matrix multiplication. All those things I'm asking you to take on faith, but it's even though it seems simple, the running time at least is high. Correct? So people missed out the crucial thing, which was BFS, and we will come to DFS later. So we will do something called breadth-first search. In order to achieve this UV reachability. And what is breadth-first search? So in simple terms, you start with U, correct? You say color U, okay? And then you explore its neighbors. So U has some neighbors, U1, U2, U3, and so on, which are the entries of the row of AU. AU comma star equal to 1, UI equal to 1, if and only if U comma UI belongs to the edge set, correct? So the neighbors are the non-zero entries of the row U, correct? Are you with me?
Yes, sir.
So you explore the neighbors of, so you explore U, which is like coloring the neighbors of U and then taking out one of the neighbors, exploring it, meaning coloring all its neighbors, and then doing it this thing. So you never color a neighbor twice. If it's colored, you do not consider it again. And so basically, what are we saying in this graph? How would we do it? One second, let me copy the graph. So you start with 1. You color 1. So you have colored 1, and then you explore 1, meaning you the neighbors of, what are the neighbors of 1? In this graph, they are 4 and 3, correct? So 4, 3 color, and now you so this part is, so no, I'm not structuring it well. I should say you first take a vertex 1, correct? And you mark it, you color it, correct? Now you take out a colored vertex. So you initially color 1, and then you take out a colored vertex in your list and explore it. So by exploring, I mean you put its neighbors 4 and 3 and you color them. So you color them, correct? Now you take out one of the colored vertices, say 4, and you explore its neighbors. So you look at what are its neighbors, 1 and 3, correct? Both of them are already colored, so you will not, the exploration doesn't put them back again. Now you look at 3 and you look at its neighbors 1 and 4 and you put them, they are already colored, so the exploration is complete from 1. So now you know that 1 can reach 4 and 3, but it cannot reach any other vertex, correct? Everything that is explorable from 1 has already been explored, and 7 is not one of them. So you know that 7 cannot be reached. That is the basic idea we will do, correct?
So in terms of matrix, we can just take the 7th column and come down that column toward the row, and all the occurrences of 1 will indicate the neighbors of 7. It will take n
Yes.
square. Right? That is
It
exactly
is still, in a matrix, it is still n squared, yes.
n cubed, because we just can't, for first occurrence of 1, we will have to take the other occurrences of 1 as well.
So you have yeah, it is order mn. Yeah.
Okay.
Not order mn. Why do you say?
I think n cubed, I think, because
why is it n cube? You are, for every vertex, you are processing the, you are exploring the vertex only once, correct? In the exploration, you look at all its neighbors. There are order n many of those, correct? And you do this for each vertex, for all vertices.
Okay.
And
Yes.
each one is, has, there are n vertices, so you take order n squared, correct?
Yes, yes.
Now this can be reduced if the graph is sparse, you can reduce this, but we will talk about this next time. So next time we will basically cover breadth first search, a formal description of breadth first search. Correct? Now, any questions?
Sir, what will be the syllabus for the mid-sem?
There is no mid-sem.
Oh, okay.
I had announced this in the beginning. There is no mid-sem.
Yes, it's possible I missed it. Sorry.
Yeah, sure. Sure. More questions? And in the timetable, at least when I had checked, there was no slot for APRG, correct? I just want to confirm it with you.
Yes, sir.
There is none, no?
No, in the timetable we had slots for only 4 subjects except APRG.
Without APRG.
APRG wasn't there.
APRG was not there, no?
There.
It was there.
No, sir, it was not there.
Not there.
APRG was not there.
Okay, good. So more questions? Otherwise, we meet after 1 week, correct? Okay. And there'll be an assignment today, which will be due sometime after the mid-sem. Okay. Okay. So thanks.
Thank you, sir.
Thank you, sir.
Thank you.